All right. So just a brief introduction of how this generally works. Usually I kind of open up the floor at the beginning for like questions that you guys have regarding the material. And a lot of the times people don't have specific questions. They just kind of want to see how problems can get worked through. So then we work through some problems together from the sections and just kind of like make sure that everyone knows how to problem solve, like what we've been learning recently. That being said, does anyone have any specific questions about what we were doing this week, which, unless I'm horribly mistaken, was sections 1.3, 1.4, and 1.5. I'm seeing nothing in the chat box, so I'm going to assume that's a no. Also, the chat box is kind of our main method of communication, which kind of makes it hard because you guys are typing and I'm speaking and it just like can get weird sometimes. But if you guys really want to turn on your audio, feel free to do so and ask a question like that. If not, just feel free to use the chat box. This is a guided study group, so I do like it when people like talk to each other in the chat box. And that being said, make sure that when you're in the chat box, you are messaging everyone, not just me. Sometimes we have it so that every individual student is messaging me instead of talking to each other as well. So the hope is that everyone can learn from everyone. All right. If there are no specific questions, then we'll just kind of get started with section 1.3. Let me figure out what problems we're going to be doing. You guys have answers in your book to odd problems, correct? Is it sections 1.6 to lesson 2? Okie dokies. To get to the right section. Sorry, my computer's lagging a little bit. Not sure what the deal is there. I am looking at lesson 2, logarithmic functions, exponential growth and decay, periodic functions. That will be, you're right, that will be 6 through 10. All right, so let's do section 6 through 10 and not 3 through 5. Is that right, everybody? That makes sense to everybody? I just got mixed up on my weeks. Sorry about that. Awesome. All right, so we will start with 6 then. All right, so just out of curiosity, who here is kind of familiar and comfortable with logarithms, especially natural logarithms? Anyone? You guys are kind of doing okay? All right. So it is pretty important for you guys to be able to work with exponentials and logarithms. In some earlier math classes that you guys may have taken, it was less important, but here it's like we're going to be using these later on when we're taking derivatives and stuff. So it is important for you guys to kind of understand and be able to work with these. Let's start by doing problem 6, which is, this is section 1.6, and this is on page 50 of you guys' textbooks. And that looks like this. All right. So what is the first thing that I should do with this problem? Any ideas? Okay. Our instructions are to solve for t. So we're trying to get t. We have a suggestion to take the natural log of both sides. But we also have a suggestion to simplify and then take the natural log. And it's always a good idea to simplify as soon as you can, so you're not dealing with tons and tons of numbers. So we're just going to divide both sides by 25 to start off with. So these cancel out, and we end up with 4 is equal to 1.5 to the t. So now we're going to be able to simplify. So yeah, you guys right on the money. Take the natural log of both sides, so we end up with natural log of 4 is equal to the natural log of 1.5 to the t. We know about our rules of logarithms, and that's if something is in an exponent inside the logarithm, we can move it to the outside. So just a little side note, a reminder that the natural log of 1.5 to the t is equal to t natural log of 1.5. So that's what we're going to do here. We have natural log 4 is equal to t natural log 1.5. And we're just going to divide this out. Can we simplify this any further using our rules of logarithms? Nope, you got it. Sometimes it is tempting to try to simplify this into the minus. There was a rule that says the natural log of like a over b is the natural log of a minus the natural log of b. But this is when the whole, this division thing is happening inside the one natural log. This cannot be simplified. Because this rule does not apply when we have natural log 4 divided by natural log 5. All right, awesome work, guys. All right, still on page 50, let's try number 12. Here, we're just kind of working with letters. This is just kind of a very general case. If we have A is equal to B to the T, and we want to find out what T is, we're just going to do exactly what we did up there. Take the natural log of both sides. And then we're going to divide by the natural log of B. So T is equal to natural log of A divided by the natural log of B. And as we said earlier, can't simplify that, so we're done with number 12. Okie dokies. Let's take a look. What about question 14? This is 2p is equal to p e to the 0.3 t. All right, what is step 1 here? Just like before, we're going to want to try to simplify. What do you mean by convert to e? Yes, we have a suggestion to divide both sides by p, and that's what we're going to do. Because in this case, p is some number, and we can take p out of the equation, and that makes the whole thing just much simpler for us to solve and capable for us to solve. So now we have this, and we know how to solve this. We take the natural log of both sides. We can move the exponent outside. So we have 0.3t times the natural log of e. We know that the natural log of e is equal to 1, because natural log and e are basically inverses of one another. So this is just 0.3t times 1. We don't have to really think about that. This is the natural log of 2. Divide both sides by 0.3. And t is going to be equal to the natural log of 2 divided by 0.3. How are we faring with this kind of problem? Are we doing okay with thinking about solving it? Awesome. All right. So a lot of these problems in the first section, problems 1 through 16, are just like practice and getting comfortable with natural logarithms, rules of logarithms, that sort of thing. Then we are going to do problem 18. And we're still on page 50. All right. So here we're given an equation. P is equal to 7.7 times 0.92 to the t. And we're asked to identify whether it represents exponential growth or decay. We're also asked to identify the initial quantity and the growth rate and state if the growth is continuous. All right. So growth or decay? Decay. How can you tell? Yes. It's less than 1, but yeah. This number in here is less than 1. I guess let me check real quick to see exactly what format they have you working with right now. Sometimes you can think about this as like 1 plus a or whatever, or 1 minus a. I tend to think about it in terms of, is this number right in here greater than or less than 1? If it's less than 1, I know that I'm looking at some sort of decay. And if it's greater than 1, then I know that I'm looking at growth. Okay. So what is the initial quantity? $7.7. How do you know that? Yes. So what we're going to do is, this is a function p of t. And what we're going to find is p of 0, or what is the population when the time is equal to 0. And that's going to be our initial quantity. Sorry, I tend to think of these as population when it's p and t, because, I don't know, it just kind of fits. And populations also often follow these exponential kind of equations. So p of 0, when t is equal to 0, what is p? That is going to be 7.7 times any number to the 0 power is going to be 1. 7.7 times 1, so that's going to be 7.7. So you can just look at this number and say, yep, there it is. That's our initial value. But at the same time, it's important to kind of understand that initial is when t is equal to 0. All right, so what is the growth rate? Yep, we're decaying at a rate of 8%. Sometimes the language here can be pretty confusing, but it's always like easiest if you're just like explicit, because you can also like sometimes they'll say, oh, the growth rate is a negative 8% growth, which means it's decay, because if it's negative growth, it's decay. And I honestly can get very confused like that. So what you said in the chat box is exactly right. It's an 8% decrease, 8% decay. Just like make sure you specify every time whether you're talking about it getting larger or it getting smaller. And that will kind of save you from confusion later on. So that's good. All right. Cool. All right, any questions regarding this problem? All right. Let's then do, sorry, I've got a list of problems that I want to do. Let's then do number 26. All right, so these problems are pretty important here. Here we're given something in the form p is equal to basically p naught a to the t. And we're supposed to put them in the form p naught e to the kt. So these are two forms that are basically situated to make your life easier or harder, depending on which form you're kind of working with. Some information is easier to discern based on the form that you're in. I'm actually going to write out the problem now. So in this form, we're able to tell very easily that we're growing at a rate of 70%. But this is not the easiest form to work with, because as people working with math, we tend to like things that are in E and natural logs. So we're going to put it in that form so that later on it can perhaps be easier to work with. All right. So we know that P is equal to P naught A to the T. And we know that it is also equal to P naught E to the K T. All right? So that's basically where we're going to start from here. We're going to say that we know this is P. And we know that this is P naught. So we also know that this is P naught, 10 here in this case, E to the K T. So now we're just going to throw out that P. We don't need that anymore. We're just going to divide both sides by 10. And that will simplify it. So what we have is 1.7 to the T is equal to E to the K T. And so in this equation, we are solving not for T, because we know that T is going to be a variable, and that's just something we're coming to terms with. We're solving for K. And once we find out what K is, we can put it in this form, P naught E to the K T, because these are the two actual numbers that we need to do that. All right, So we're going to do as we were doing earlier. We're just going to take the natural log of both sides. So we're going to end up with t natural log of 1.7 is equal to kt natural log of e. So this is t natural log 1.7 is equal to kt, because this is equal to 1 right here. I'm going to divide both sides by t. So I know that k is equal to the natural log, cross this out, of 1.7. So I can go back and put this in my original equation. I'm going to say that p is equal to p naught. In this case, we know p naught is equal to 10. E to the k times t. And so we know that that is equal to 10. All right. So it is pretty important that you're able to go between these two forms of an exponential function with relative comfort. Would you guys like to try another one of these problems? Let's maybe do like 22. So same principle, we're just kind of doing the opposite thing. We have p is equal to 2e to the negative 0.5 t, which is equal to, what is this going to be equal to? We're going to identify our p naught. And we know our k is equal to negative 0.5. So if we're going to put this into the form p naught a to the t, we're going to put it in like this. And then I'm going to divide both sides by 2. So I'm going to end up with e to the negative 0.5 t is equal to a to the t. Yeah? Then what am I going to do? Yep. So negative 0.5 t ln e is equal to t ln a. Cancel out those t's. Don't need that. So I know that the natural log of a is equal to negative 0.5. But I want actual a. So I'm going to just take it to the e. So I'm going to end up with a is equal to e to the negative 0.5. Which is pretty familiar. There's another way we could have done this without using natural logarithms. We could have been at this point where we said that e is equal to negative 0.5 t, and this is equal to a to the t. And we can separate this out. So each of the like if you have something that's like multiplied up here, the way that you do that is you can also write it like this. Because of our rules of exponents, you guys went over these, right? Like if you have, I'm trying to come up with letters that we're not using right now. If you have like b to the m to the n, it is equal to b to the m times n, right? So this is rules of exponents. And so we can write it like that. And then we're just going to keep this as a to the t. And we know that this, because it's a number to a number raised to the power of another number, there are no variables involved in this right here, is just going to be a number, and that's what we're looking for a. So this number to the t is equal to this number to the t, so a has to be equal to e to the negative 0.5. Does that make sense? Yes, no, maybe so. Awesome. So you saw like the two kind of different ways that I worked through this, what a had to be. One using natural logs and one doing like rules of exponents and basically working through it like that. Cool. Any questions about this? Otherwise, we can kind of move on to 1.7. Got some fundamentals out of the way. Not seeing any, so I'm going to move on to 1.7. Okay. Solve for the actual number of the natural log in any of these problems. Do you mean like, will they give you like the natural log of 4 and then tell you what is this? No, they're not going to do that. That's ridiculous. No. This is a perfectly acceptable answer. Yeah, that is perfectly acceptable to put in your answer. So yeah, okay. Let's do, yeah, that would be so hard. Oh my goodness. If they asked, you're just like, oh, couldn't imagine. Yeah, no, I don't like that's what we have calculators for, to put natural logs in there. Okay, let's do 1.7. I'm on page 57 right now, and we're going to start with problem 2. Problem 2 goes, the exponential function y of x is equal to c e to the alpha x satisfies the conditions y of 0 is equal to 2, y of 1 is equal to 1. So our goal here is to find c and alpha. And y of 2. All right. So where do we start? What is our first move going to be? First move I see is we're given an initial value here. This is where t is equal to 0, or x in this case, x equals 0. So that's going to make things pretty easy, because we know that y to the 0 is equal to 2, which is equal to c e to the 0. E to the 0 is equal to 1. So we know that c is equal to 2. So that's just kind of where we're going to start. We're going to pick off one of these variables that we know we can work with. So c is equal to 2. Next, we're going to try to track down what alpha is. Y of 1 is going to be equal to 1. And so that is going to be equal to c e to the alpha x, or in this case 2 e to the alpha times 1. So what I'm looking at here is 1 is equal to 2 e to the alpha. I'm going to divide. So I have 1/2 equals e to the alpha. Then I'm going to take the natural log of both sides. So I'm going to end up with natural log of 1/2 is equal to natural log of e to the alpha, which is equal to alpha times 1. So we know that alpha is equal to natural log of 1/2. The interesting thing about the natural log of 1/2 is that a lot of the times it's actually written as the negative natural log of 2. And the reason that is just because of log functions, like rules of logarithms. This, we can use that a over b rule for. So this is the natural log of 1 minus the natural log of 2. And the natural log of 1 is equal to 0. So 0 minus the natural log of 2 is the negative natural log of 2. So a lot of times we don't leave it in ln 1/2. We actually write it down as the negative natural log of 2. But either is correct. So you can leave it however you feel most comfortable. So I'm going to put it as the negative natural log of 2 because I went through that. Alpha is equal to the negative 2. All right. So now we get to find y of 2. So y of 2 is going to be equal to 2e to the negative ln 2 times 2. And that is going to be some number. If we have a calculator, if you guys have one on you right now, you can figure out what that number is. But there are no variables in this, and it's going to be a number. So I would leave it like this, just because a lot of the times you don't have calculators, especially on like quizzes and tests and stuff. And so on a quiz or an exam, perfectly acceptable answer to leave it in terms of e's and natural logs. All right, any questions? Nope, got it. All right, so let's also do do you want to do another one similar to this one? Or, okay. Do you see a problem like this in the book? Let's see. Yeah, we'll just do this exact same format. I'll just change up what this is. Give me a sec to erase all of this. All right. This is a problem that at least my professor was a fan of, this type of problem. So I'm going to throw in some other numbers here. Y of 0 is going to be 12, seems like a good number. And y of 1 is going to be 3.5, because why not? Okay, so we're going to follow the exact same kind of step process. We're going to start by using this initial value. We're going to say that when y of 0 is happening, we're looking at our initial value. So we know that's equal to 12. We know that's equal to c times e to the 0. Alpha, well, e to the alpha 0, but e to the 0 is going to be 1. So c is going to equal 12. Okay. Just a reminder that this is not actually what's in the book anywhere. I'm just throwing in some random numbers. So if you're looking for where this is in the book, it's not. I just thought we could do it for practice. now let's go through and find out what alpha is. So y of 1 is equal to 3.5, which is equal to 12. Actually, yeah, let's leave it at 3.5. Why not? Which is equal to 12 e to the alpha x. And we know here x is equal to 1, so that's 1. So we know this is, let's divide both by 12. 3.5 divided by 12 is just put it into my calculator. It's some number with an obscene amount of decimal points. 0.29166 repeating. And so that's going to be equal to e to the alpha. So we're going to take the natural log of this, which is 0.29166, and the natural log of this. And we know that this is equal to 1. I don't know why I wrote a minus sign instead of a 1. So we know that alpha is going to be equal to the natural log of 0.29166 repeating. And I'm actually going to find out what that is. Okay. So this is equal to negative 1.232. So that is what alpha is. Okie dokies. Is everybody good with me up until this point? That being said, they won't give you a problem like this on an exam because you can't solve that. You would be taking, like, you would have to leave it, not simplify it out into this decimal point if you were to be given something like that, because it seems wrong. And you also would not be able to find what the natural log is. But because we have a calculator with us right now, or at least I do, we can go ahead and run it. So y of 2 is going to be equal to 12 times e to the negative 1.232 times 2. And so that is going to be 12 times e to the negative 2.464. And we can go ahead and figure out exactly what this is going to be, because why not? So that is e to the negative 2.464. This is 12 times 0.08509, or y of 2 is equal to 1.02. All right, does this answer kind of make sense? One way to kind of like think about it is that we start off with a high. We start off at 12, and then as x gets larger, it goes down. And then if x gets larger again, this answer is going to be lower. So y of 0 is greater than y of 1, which is greater than y of 2. And so that makes sense. We have decay here. And alpha is negative, so that makes sense also with the decay. So everything here makes sense. So we can feel confident that we at least approach the problem in the right way. All right. Let's do next let's do number 8. So again, here we are on page 57, doing number 8. Find the doubling time of a quantity that is increasing by 7% per year. All right. So how are we going to do this? We need to make an equation that makes sense, that will help us find our answer. Okay, well, doubling time we know is going to be 2 p naught is equal to p. And we have p naught. Should we use e to the kt or should we use a to the t? What should I put in here for our function? A to the t, exactly. So we have 2 p naught is equal to p naught a to the t. We're just going to divide both sides by p naught here. So now we're still looking at doubling time, but we have 2 is equal to a to the t. Simpler equation. What is a? We've got a percentage at which something is increasing. So we're going to be looking at, yes, 7% is what it's increasing at. So a is going to be 1.07. So this is going to be getting larger as time goes on. All right. So what are we solving for in this equation? We're looking for doubling time. So we're solving for t. Let's just take the natural log of both sides. And we end up with t is equal to the natural log of 2 over the natural log of 1.07. And that is a perfectly acceptable answer for doubling time. If they ask you this kind of thing on an exam, this is what your answer would look like. But for now, I'm going to put it into a calculator so that I can kind of understand what this time actually looks like. If I can work my calculator, which I guess is doubtful. Natural log of 1.07. So t is equal to 10.2. And that's what our doubling time is. I have a question. How did I get 1.07? Okay, so basically what's going on in the anatomy of p is equal to p naught a to the t. This a, let's think about it if a is equal to 1. If a is equal to 1, it is not growth nor decay, because p is equal to p naught whenever t exists. If we had a very, very large t, if say t was 100, then this equation would look like p of 100 is equal to p naught times a is equal to 1 here, so 1 to the 100. 1 to the 100 is just 1. 1 to the anything is 1. So if, regardless of what this is, regardless of what t is, p is always going to equal p naught. So there's going to be no change. So that's the case of a is equal to 1. Now, if we think about a being less than 1, let's say that a now is going to be 0.92. what's happening here is that if t is equal to 1, then p is going to be less than p naught, right? Because what we have here is p of 1 is equal to p naught times 0.92 to the 1. So if we have some number here times this decimal, which is smaller than 1, we end up with a smaller number. So here p is less than p naught. What happens if I turn this 1 into a 40? What happens to this number in here? It gets really tiny. So that's 0.92 to the 40, which is 0.035. So p is very, very small in compared to p naught. So what's happening here is that as t gets bigger, p gets really tiny. Yeah? So how I tend to think about a is default a is equal to 1. So if a equals 1, then nothing's happening. If a is less than 1, then it's decay. And it's decay at a rate of, here the decay rate is 8%, right? Because it is 1 minus 0.08, or 8%. Are we good with that? This is true? Nobody's saying anything. Awesome. Cool. So this is true. We're A-okay with that. So I've got that default a is equal to 1. I know if a is less than 1, then I'm looking at a decay. And now let me think about what happens when a is greater than 1. I have growth. Because I will have p, and I'll have t, and my graph will look something like this, because as t gets as t gets larger, p gets very, very large. And I'm still going to think of a as a default of 1. In this case, it's going to be 1 plus whatever percentage, right? So if I have 1, which is no change, and then plus 7% change, so it's growing at a rate of 7%. I'm going to translate this from percent into like actual decimal points as 0.17. Or, yeah, 0.07, excuse me. That would mean that a is equal to 1.07. Did I explain that thoroughly and in a way that you guys understand how I got 1.07? Okay, good. It's basically just like, how am I changing the initial like state? All right. Let's move on to section 1.8 because we've got a lot of ground to cover today. Sorry, usually I like to like focus in a little bit more, but we have 1.6, 1.7, 1.8, 1.9, and 1.10 to do today, and usually these shindigs last like an hour, and we've been at it for about 50 minutes. So I want to be sure we get everything. So for section 1.8, let's start off with 4. And this is on page 63. And this will come in handy later when we're like thinking about like composite functions. We're thinking about how functions fit into one another later on in this class. And it is going to be important for solving those kind of problems. So what we're given is that f of x is equal to x squared, and that g of x is equal to 3x minus 1. So for problem A, we are being asked to find f of 2 plus g of 2. How are we solving this? Well, we know what the function, we know what the function f is. So it's x squared. So this is going to be 2 squared plus 3 times 2. Put it in brackets, but really don't need to now. Minus 1. So it's going to be 4 plus 6 minus 1, or 9. All right. So B, we are looking at f of 2 times g of 2. Same kind of principle, plug 2 into both of them. F of 2 is going to be 2 squared times g of 2, which is 3 times 2 minus 1. Here we have 4 times 6 minus 1, or 4 times 5, which is 20. All right. C. Now we have f of g of 2. What is the first thing we're going to find right now? G of 2. Precisely. G of 2 is equal to 3 times 2 minus 1, which is equal to 6, not 4, minus 1, which is equal to 5. All right. So if g of 2 is equal to 5, then what we're going to do here is f of g of 2 is equal to f of 5. Because as we said, g of 2 is equal to 5. Here, I'm going to separate this out by color, actually. Maybe it'd be a little easier to visualize. So this is f of 5. And the way we're going to do that is just put it right back in. So f of 5 is equal to 5 squared, which is equal to 25. Ta-da! And finally, we are going to track down g of f of 2. And so we're going to use the same principle. We're going to say f of 2 is equal to 2 squared, which is equal to 4. So g of f of 2, which is 4, it's g of 4, is equal to 3 times 4 minus 1. All right. Any questions about this type of composite function work? Awesome. Yeah, this stuff is pretty good, usually. It's just a matter of like making sure that you guys like keep track of everything. I'm going to say this a lot in this course, but I write everything down. I never assume that I know what I'm talking about. I always just write down this is equal to this so I don't confuse myself later on and can like backtrack and look at my work. Okay. Let's do a little bit of 1.9 and 1.10. All right. So for 1.9, I always thought this section was a little bit weird. This is page 69. And we are going to do problem 4. So this is y is equal to 3 over x squared. So it's asking us to determine whether or not this function is a power function. And if it is a power function, to write it in the form y is equal to k to the xp and give the values of k and p. There's one big takeaway from this problem. First of all, is this a power function? Yes. What is k and what is p? K is equal to 3, exactly. So I'm going to write it in this form. I'm going to say y is equal to k, which is 3, x to the p. So what is p? -2. Exactly. The big takeaway from this is that 1 over x to the 4th is equal to x to the -4. And you guys should be fairly comfortable just switching these out as need be. So that is the big takeaway from this problem. Let's also do problem 8. I don't know why I cleared that. I didn't really have to, because we got plenty of room. All right. Is this a power function? Yes. What is k and what is p? I'm going to write this in a form that's easier for me to just kind of analyze. So k is not actually equal to 5. K is going to be equal to, this is kind of putting it in a form more similar to the power function, in that k is going to actually be equal to 5.2. And so that leaves us with figuring out what p is. Anybody have a guess at p? -1/2, exactly. You got it. And so that rule there is that if you have the square root of x, the square root of x is equal to x to the 1/2. And so here we have 1 over the square root of x, so it's kind of a combination of both this and what we just did in the last one, in that it's -1/2. So exactly, you guys got it. Perfect. Cool. Let's also quick do problem. Let's do problem 16. So this is the proportionality stuff. And basically, what proportionality is kind of referring to is like how do certain variables relate to certain other variables. In this case, we've got F, which is force between two bodies, is inversely proportional. And I was taught to use this sign to mean proportional. So I'm going to first write it out like that. So that for me is just another way that you could write this is F is equal to K. So any constant times whatever this is. This is probably a better notation for this class. I don't think they use that notation. So we're just going to use this, actually. Ignore what I said 30 seconds ago. This is what we're going to use. So F is inversely proportional to the square of the distance d between them. So how am I going to do this? So what we're doing is we're relating the quantity f to the square of the distance d between them. So d squared. So relate them for me. Put it in an equation. How are these related? Does it look like this? Or does it look like this? The first one? Why the first one? Yes, but we do say in the problem that they are inversely proportional. So it is actually going to be the second one. Yep, for the exact reason that you stated. This is going to be the answer, the second one right here, because they are inversely proportional. So it's going to be F is equal to K. And I always write it out like this. You can write it like that if you want to, but I write it like this so that I can clearly see that it's inversely proportional and dividing. All right. So let's do some 1.10. Periodic functions. Trig is fun, isn't it, guys? Don't you all love trig? Yeah. Okay, so my very first year running a GSG, somebody basically asked me to just do all of trig in one go. And I'm going to see if I can find the video for that so that maybe you guys can watch it if you haven't had trig in a while. But it took 2.5 hours, so I'm not going to do that now. What I am going to tell you is that the easiest way to get through this and this part of the class, you don't necessarily need to like fully understand trig functions. And I'm not saying that as like a, you can just like go ahead and just kind of like BS your way through it, because it's like important that you are capable of understanding this, but this class does not require you to go ahead and take a whole trig class in order to get through this section. Trig functions are, number one, a pretty small part of this class. They are going to show up in problems, and it is important that you kind of understand like what a graph of them looks like and how they kind of relate to one another. But most of the stuff that you need to know about trig functions will be taught to you in this class. That being said, it is going to take a little bit of just like brute force memorization. just a little bit, especially this on page 74 for this section. I always would encourage you guys to go and fully understand exactly what's going on with this material, but time-wise, that is sometimes just not an option for you guys in this class. So this equation, knowing that A is amplitude, B, or rather 2 pi over B is period, and vertical shift is C, is what you need to know about these equations. Okay. So, that being said, you are going to need to know this, especially for this section, and for kind of understanding trig functions and how they work. Let's do some problems from this section. So now we're going to be on page 75. And let's start off with problem 2. And here we're just going to, it says to graph the function and define the amplitude and period. So we are going to graph this function. All right. Oops, that's not a vertical line. That's also really poor. Thank goodness for straight line functions. Okay. So, the best way that I can kind of do this is just kind of walk through. Y is equal, we're going to start off with y of 0 is equal to 4 cos 0. And the generic cosine wave looks like this. 1 period of the cosine wave. So we start here, 1, we end at 1. This is going to be -1. It's a little off on scale. This is pi, and this is 2 pi. Right? So we have these big important points. At 0, the point on the cosine graph, the standard cosine graph, is going to be 0, 1. We also know that there's the function, or the point on this graph that is pi, x is equal to pi, y is equal to -1, and the point x is equal to 2 pi, this is equal to 1. Okay, we also know that these points are halfway between them, so those points include pi over 2, 0, and 3 pi over 2. 0. Okay. So, I know that this point is going to be up here somewhere. I know that the cosine of 0 is equal to 1. So this is going to be at 4. And that's going to kind of inform how I draw the rest of this graph. So I have a big old point right here. Then I'm going to do y of pi over 2. So this is going to equal 4 times cos. Pi over 2 times 2 is going to be pi. The cosine of pi is going to equal -1. So at pi over 2, this is going to be 4 times -1, or right here. And then I'm also going to plot the point y is equal to pi, or not y is equal to pi, excuse me, y of pi is equal to 4 cos 2 times pi, which I know is going to be equal to 1. So at pi, this is going to be the x-axis, by the way. Just going to label that. I'm all the way back up here at 4. So you can kind of see how this is kind of sketched out. I can draw like a very like light line kind of in between these points right now. And I know that this is going to be pi over 4 and 3 pi over 4. And I know that because it's just like halfway between type thing. So what are we kind of noticing here? What we're noticing is that we have a vertical stretch. Our amplitude, not shift, bad linguistics there. I took this regular cosine graph and I went from a vertical range of 1 to -1 to 4 to -4. So I stretched the graph upward, and that is an increase in amplitude. And that corresponds with this equation that we know that we have, which is y is equal to a cos b x. So this 4 is going to be my amplitude. And amplitude is simply the distance from the highest point of the graph to the x-axis, and then the lowest point of the graph to the x-axis, or the middle point, rather. If there's a vertical shift, it's not like going to the x-axis. So one easy way to think about amplitude is that what is the distance from 4 to -4? It's 8 units. I go down 4, and then I go down another 4. And the amplitude is going to be halfway, or the amplitude like line is going to be like halfway in between there. So if this was shifted upward a little bit, the amplitude would still be 4. So this whole distance divided by 2 is the amplitude. That being said, this b here is going to be referring to the period. We know that the period of this is 2 pi. We have one wave every 2 pi for the x. So the period here is going to be 2 pi divided by b. In this case, it's 2. If b was equal to 1, then the period would be 2 pi, and we'd be looking at a regular cosine graph. But it's not. We eliminate those 2, so we know that period, which is often also said t, is equal to pi. So our period is equal to pi, which means we have one graph going through one cycle, and in the distance of between 0, x equals 0, and x equals pi. So this is our period. So yes. Does anyone have any questions about how this kind of happened? I'm sure there are a lot of like trig-based questions, which is stressful, I know. I don't think they're going to make you do any graphing. I just have a tendency to think that you can learn a lot from graphing things and kind of visualizing them. So that's why I did this problem in particular. So you can kind of see how a generic cosine graph gets altered by these numbers. So we bump up the amplitude, and the period is, as we would say, inversely proportional to B. So if B gets big, then our period gets smaller. Is everybody okay with what I just did? Okay. That's good. All right. I know this is not the most digestible section, and I know it can be really stressful to like look at this and be like, oh no, trig, I haven't had trig in so many years. Why are they making me do this? But it's gonna be fine, I promise. Okay. I'm kind of running out of time. Is everybody okay? Do we have any more questions? I'm seeing silence in the chat box. No questions? Okay. If you guys think up any questions relating to this material, last week's material, any other material, feel free to email me. I'm always available via email. So yeah. Thank you guys so much for coming. I hope you guys picked up some interesting information regarding this material, and I will see you at this time, well, 5 o'clock Eastern Standard Time next week, Sunday. All right, you guys have a great night.